3.4, and it deals with a new class of functions, and these are called our exponential functions. We're going to generalize the idea of an exponent. Now, you did a little bit of that in your intermediate algebra. So we're going to define a function that looks like this. Some f of x is some number b, call that the base, raised to now a variable. Now, where did that come from? Well, it started out as an exponent. For example, say b was 2, and you had 2 cubed. That would just be 3 factors of 2 multiplied. Really easy when it was positive. Then we also learned that, okay, say if it was a negative value. Okay, what was that? Well, remember what you could do? You could write that as 1 over 2 cubed, using your rules of exponents, which is 1 over, now multiplying. So this is 8, this is 1/8. So we learned how to put positive values, integer values, negative integer values. We even learned how to do fractions. For example, you could 2 to the 1/2, meaning I'm putting different values of x over here. And that was, we learned, was nothing more than the square root of 2 gave us a strange result. Now we know what it means, so we got, 1.4142, etc. So we could put fractions in there. Well, now we're extending it even further. At least we knew kind of what this meant, but we're extending the idea of an exponent. So what I'm presenting here is not that trivial, because now we're looking at things such as 2 to the square root of 2. What does that mean? How can I have square root of 2 factors of something? It's kind of a strange result. And the other thing that is strange is we could take, for example, I could take the number -2, and I could, square that, and I get +4. I could take the number -2, and I could cube that, and I get -8. So I can have a negative here. But if I want to treat this as a function, that becomes a problem. Because what happens if I looked at this as having b is -2, sometimes it's positive, sometimes it's negative. Sometimes it's undefined. -2 to the 1/2 is undefined. That's the square root of a negative number, which is not defined. So we have to put some restrictions on b. b has to be strictly greater than 0, cannot be negative, to avoid all this. But now, this is our definition, and we are not going to go and thoroughly try to understand this. How can I take x to be a irrational number? I could even look at 2 to the pi, any number I want. What does it mean to have pi factors? We know pi is 3.1415, etc. So that is a higher level course than this. So we will just take this as a definition. We'll make sure that the base is positive to avoid all these strange things, because we'd never be able to find the domain over here, because there's just all these excluded values, and we'd be bouncing around. Sometimes it's positive, sometimes it's negative, sometimes it doesn't exist. So we just get rid of that by looking at that. When we include that, and we look at an example, we start to see what this function looks like. So if I look at f of x is 2 to the x, again, 2 is greater than 0, so let's put that into our calculators. I'm going to use Desmos as my calculator, because I find that's a nice and effective little tool to use. And you see what we get. So now I have y equals 2 to the x. That's what I get. That's what the picture of my new function looks like. In this range over here, I'm dealing with negative values. So you can see why it is less than 0. Let's take a look at a few values, x and y. Well, first off, we can put in 0. Okay. 2 to the 0, that's one of my rules of exponents, that's 1. So its y-intercept is at 1. I can put 1 in, I get 2. I can put 2 in, I get 4. 2 squared is 4. I can put -1 in, and I get -1/2. You see, not negative, 1/2, excuse me. I can put in -2, and I get 1/4, because I'm putting that in. So I put in, for example, 2 to the -1 is 1/2. 2 to the negative 2 is 1 over 2 squared, which is 1/4. So when I go to the left of 0 on the number line, you can see what's happening here. It gets smaller. You know, smaller and smaller and smaller. So there it is at negative 2. That's 1/4 of the way over here. And we just kind of keep going down and down and down, etc. So that's what the graph of my exponential function looks like. And if I change it and say, and put a new one, say I do 3, so y equals 3 to the x, looks very similar, just a little slight, 3 to the x, excuse me. I get this. They both do pass through the same coordinate, 0, 1. Right there, that's my 0, 1. No matter what base I have over here, so I have y equals 10 to the x, I get the same thing, the same base. Although it looks a little bit different on either side, the same base. That's a common feature of exponential functions. They have this common y-intercept over here that we look at. Okay. So we have all these different potential bases. Now if I try to put in a negative base, I'd say y, equal to, say, negative 2 and raise that to the x. It's not going to let me do that. It's going to, not give me anything. Doesn't display anything. Nothing new has happened. It doesn't understand what to do because it's not a function. So I can't have that. My base has to be positive. Okay. So we can evaluate these functions for different values, etc. But that's what we're kind of faced with. What I want to end with now is, well, let's take a look at that. While we're dealing with it, let's take a look at the domain and range. Let me do that. Kind of keeping my eye out on the clock over here. From that picture, we get a sense for the domain. So there's my function. So I have my function over here. F of x is b to the x, where b is greater than 0. If I want to look at the domain of that, I notice from the graph, I could put any value in for x. So domain is, the set x is any real number. It can be any real number. Because I can always put a number in here. Now, interpreting what it means to put pi there, that's a different story. But if we think of it, we can go through and define that, but takes a lot of work. The range, however, was different. Let's take a look at the picture and notice what you get. Notice, no matter what value of x I put in there, I will never get a negative value out. B is a positive number. Take a positive number, raise it to a power, I can't get negative. So over here, the range, that depends upon the y, that will always, it's a real number, but it's always going to have to be greater than 0. Now, I can't get 0. What I have to do is evaluate this for x equal to negative infinity and take b and raise it to the negative infinity power. That's 1 over b and infinite number of b factors, which would give me 0. So it's never quite 0. And you kind of saw that in the graph. So here's my y-intercept that was always here. And my function looks like this. This goes off to plus infinity, so that's x is any real number, or my y goes to positive infinity. But here, it gets closer and closer to, but it never gets to 0. So it never equals 0, because I'd have to go all the way out to here, and x going to minus infinity. Plus infinity for x would give me 0, infinite for that. So the domain and range for that is of that form. What I want to close out with, however, is one interesting base. There's a special base that comes up naturally. This is the natural base. And we'll close out with that today. And this comes from, if you wanted to do continuous compounding. There's a way of looking at what we call continuous compounded growth. I don't know if I'll have enough time to do this. I'll get it started. We'll finish it on tomorrow. Continuous compounded growth. So it looks like that. You have A is equal to some A0, 1 plus R over N raised to the NT. Where in this case, A0 is your initial amount. N is the number of compoundings per time period, this is how money grows in a bank, if you're curious, or how populations grow, or how the virus, the COVID-19 virus spreads by something like this. Number of compoundings per time period, T. T is the time in whatever units. T is time. Sometimes it's years, sometimes it's months, hours, it can be whatever. Typically it's years. And R is the, rate of growth written as a decimal. Rate of growth, percent rate of growth written as a decimal. Rate of growth. So if I put that in, I could see, if the initial amount was, say, I'm investing, say, $10,000 at an interest rate of 5% compounded monthly. So for 20 years, so N would be 12, and then we're going to be looking at problems like this later on, but I'm just talking about continuous compounded growth. I'm going to rearrange that formula and write it in this way. This is what's kind of a unique aspect of what we're going to do here. And we're going to come out of this with something that's even more distinct and interesting. Okay. I want to do this. And so, let me see. I always sometimes switch them around all over. Okay. So what we're going to do is make a change of variables over there. Simple little change of variables. We're going to let N equal to, R times N. Now the number of compoundings is going to become a real number now instead of just a irrational number. Instead of just an integer. So we plug that in over here. So I have my A is A0 times 1 plus R. I'm going to replace my N with R times N. R times M now. That's where the M was. Raise that to the N times T. So it's my R times M times T. I'm going to rearrange this. Notice what happens. This cancels out. This becomes A0. And this is 1 plus 1 over M. I'm going to change the order over here. Raise that to the M power. And then I'm going to raise that to the R times T power. So I have a kind of an expression here that only depends upon M. So I have this expression. 1 plus 1 over M raised to the M power. And what I'm going to do is I'm going to let M get very large. I'm going to let it go to infinity. Meaning that's my taking regular compounding and continuous compounding is I let N go to infinity, which is equivalent to letting M go to infinity. And let's take a look at that expression. And we'll kind of see something that comes out. Let's use our calculators for that. And we'll take a look at hopefully what comes out of that. So turn on the calculator. We're just about out of, it's about a few minutes. Okay, so I'm going to be looking at this expression. Let me put it in as an expression over here. Clear this out. And I'm going to do that as an expression. I'm going to replace M with X because this has an X. 1 plus 1 over X. Okay, raise that to the X. X is just playing the role of M. Okay, then let's take a look at our table of values. So we have that function in there. Now I'm going to look at table of values. And here, as X gets larger, let's look at this number on the right-hand side. Let's look at my table set now. I want to do some different table sets. So I start at 0, and let's go, instead of 1, let's go in increments of 100. Or let's go in increments of 10. And then I go back and look at my table again and see what's happening. At 0, it gives me a problem because that's division by 0, as you see over there, because 1 over 0 is undefined. But look what happens to these other numbers. As I go down my table of values. That's for increasing the m value. Does it go and get larger and larger forever? No. You start to see it settles down. 2.71. This value that it gets closer and closer to is a special number. And it's actually called Euler's number. So this gets closer and closer to a special number. So as n gets very large, this expression gets closer and closer to 2.71828. Keeps going on and on and on forever. Just like pi, it's an irrational number. It's related to the continuous growth of things, and it's given a name. We give this number a name, and we call it E for Euler's number. Euler was a very famous mathematician who explored a lot of his properties, and is also in honor of him for that. Now, there's always been these big debates, what's more important, pi or E? So you kind of see that. This we call the natural base. So now we have a special function, a special exponential function called the natural exponential function. We'll end with that. And it's got that little button on your calculator that I'll show you in a second. So here's the natural base, and that's base E, which is nothing more than the base 2.71828. Just like pi, we have a special symbol for it. And we also have the natural exponential function. So now we have a new function. It is positive, but now it's e to the x. And it does satisfy that condition, and that's by natural exponential function. Now, for example, say I wanted to evaluate something. So say f at, say, -2. Well, that is e to the -2. Well, what is that? Well, I can evaluate that approximately here, writing it that way, or I can get a decimal, exactly, or I can get a decimal approximation simply by using my calculator. And I'm going to show you where that E button is if you haven't already seen it or are not familiar with it. So coming over here, we can see there, right behind this LN button is that E. So I do second function, E, and if I put in the number -2, that's 1 over 2.71828 squared, it essentially gives me that. So it's, the approximation to that is like 1 divided by 2.71828 squared. It gives me this relatively close approximation to that. Not exact, because I didn't take it out as many, but I'm good up until the, the 5th decimal place there. I could keep going, and then it would keep getting closer and closer to that. But that's what I wanted to kind of end with today. We now have a special exponential function. So what should you take away from today? Well, today we've introduced this concept of an exponential function. We know its domain is very simple. The domain of any real number. We can put any real number into it. We also can determine its range. The range is all real numbers that are greater than 0. The natural exponential function looks very similar to all the other ones. Now, if you look at its graph, it does the same sort of thing. So here is my function. This is like, that's, 2 to the x. That's 3 to the x. E to the x is between those two. A little bit closer to the 3 than the 2, but they all pass to that. That's my e to the x. And that's what its graph would look at if you looked at it in more detail. Okay. And you should be able to evaluate these functions for different values. Well, that's all you need to know about now. Domain, range, and then how to evaluate the different types of functions. So that being said, that's all your